A very welcome to you. Very good morning to all of you. And today I'm going to talk about the problem of hydrogen atom. So, hydrogen atom. As as we understand that hydrogen atom is the simplest of all atoms. It has a proton and an electron. So this atom is the simplest of the atoms that we have discovered till now. And uh, we have a proton and an electron system. Now, if we look at the problem of hydrogen atom, uh, it seems to have spherical symmetry. And this system, the system that is spherically symmetric, we can choose a symmetrical mathematical formulation for that problem to be solved. I mean, if we try to mathematically look into the problem of hydrogen atom, and I write down the Schrödinger's equation. Now, in this Schrödinger's time-independent equation, what we have a Laplacian operator. And this operator can be written in Cartesian coordinates as dou2 by dou x2 plus dou2 by dou y2 plus dou2 by dou z2. But if we look into the potential energy of the hydrogen atom, the potential energy has a dependence on R, and R is the average position of the electron from the central proton. And if we try to solve Schrödinger's wave equation for hydrogen atom, taking into consideration the Cartesian coordinates x, y, z, it mathematically becomes very cumbersome. It becomes extremely laborious. It's not like that you cannot achieve the results, but that's going to take a lot of labor. Now, exploiting the spherical symmetry of hydrogen atom, we can immediately think of using spherical polar coordinates to understand the problem of hydrogen atom. And in doing so, as I said, that the hydrogen atom is spherically symmetric, and spherically symmetric means that you have a symmetrical situation with respect to the radius of the sphere that you can assume as an approximation. Even though it's not an exact thing, but as an approximation, assuming a spherical geometry, we can solve this problem using spherical polar coordinates. So for that, what we have to write down this Laplacian operator in spherical polar coordinates, and we have done that as a part of tutorials. We have achieved the Laplacian operator for spherical polar coordinates, even though that's also cumbersome, but the basic equations that can transform your Cartesian system to the spherical system, we have done that in our tutorial part. So what we have obtained there is the Laplacian operator. We have obtained Laplacian operator in spherical polar coordinates. Spherical polar coordinates. And what we have for that, this del square is 1 by r square dou by dou r of r square dou by dou r. And then plus 1 by r square sine theta, and then dou by dou theta sine theta dou by dou theta. The third term we have plus 1 by r square sine square theta dou 2 by dou phi 2. This is our Laplacian operator in terms of r, theta, and phi. And as we understand that that r is our radial part of the spheroid that we are assuming, and theta and phi, they are taking into account the angular part. And even though we have two angular parts, one is our theta and another angle is phi, and phi is called as the azimuthal angle. And we understand it from the basic geometry of having that the plane of x, y, and z, and translating down the Cartesian coordinates into the polar coordinates. We understand the projection of the azimuthal angle phi and theta. So the point is that we have three unknowns. If I incorporate the Laplacian operator into the Schrödinger's wave equation, it will automatically lead to the variables which are unknown to us, the functions which are unknown to us. And if we boil down it to r, theta, and phi, in Schrödinger's equation, we will have three unknowns in a single equation. And at the same time, we understand that if we have two unknowns, we can exactly solve them only if we have two equations regarding the same types of unknowns. And we can solve the problems of what we call them as linear equations, and we can calculate the values of the two unknowns. But here, what we have is we have three unknowns, and obviously we cannot directly solve the Schrödinger's wave equation because the number of unknowns in a single equation is three. So obviously we have to look for an approximation to deal with this problem. And obviously what seems to be plausible for us is that if we can somehow manage to separate the three unknowns into three independent equations, so that the equation 1 is not dependent on equation 2 is not dependent on equation 3. So for that, what we do is we choose our wave function. So if I have to write down the Schrödinger's equation here, what I will have, this is my del square, and I will incorporate psi, and then plus 2m by h bar square times e minus v of psi is equal to 0. So this is my Schrödinger's wave equation in spherical polar coordinates. And before proceeding into the mathematical formulation, I would like to say that this problem, solving the problem of hydrogen atom, it becomes the backbone when we have to get some approximate solutions regarding the atoms which have multi-electrons in them. I mean, an atom having more than one electron can be taken as an approximation of this problem, and we can extend this problem to the molecules as well. So there are many ways that we can use this model of a hydrogen atom in solving some of the complex problems in physics and chemistry. So what the idea is that I would like to, the first job that I have is to manipulate this equation in such a way that I can have an independent equation for the radial part. I can have an independent equation on the angular part theta, and an independent equation on angular part phi. So for doing that, what we'll do is we will take on psi. We will take on psi, which is the function of r, theta, and phi, as r of r and theta of theta and phi of phi. Now, defining those functions are exclusively dependent on their respective quantities, like r is dependent on small r, capital theta is dependent on small theta, and capital phi is dependent on small phi. And for small theta, I'm using exactly q, and then you can differentiate between the q as small angle and theta as the big theta that we have. So here I must keep q. Now what am I going to do is I'm going to differentiate this equation and directly substitute those results in the Schrodinger's wave equation, which we have written down in spherical polar coordinates. So for doing that, what we can have here is we can have dou psi by dou r. That can be theta of theta, phi of phi, and then you will have dr by dr. And I can differentiate it again, and this will give me dou 2 psi by dou r2, and I'll get the same thing, theta of theta, phi of phi, and then d2r by dr2. Now, the similar kind of considerations we will take for theta and keeping r, because r and phi will act as constant for theta of theta. And if I do the same thing, what I'll obtain for dou psi by dou theta, what am I going to find is dou psi by dou theta will be, what will be out, I think r of r will be out, phi of phi will be out, then you will have d psi, no, it has to be d capital theta divided by d theta. And we can have its double derivative in the similar fashion. Dou 2 psi by dou theta 2 will give me r of r, and then phi of phi, and then we'll have a total derivative d2 theta by d theta 2. And finally, under the same action of mathematical action, we will have for dou 2 psi by dou phi 2, for that r of r will be out, and then theta of theta will be out, and inside you will have d2 phi by d phi 2. So all of these equations that we have, and what we can do is we can incorporate these results in our Schrodinger's equation that we have written in spherical polar coordinates. So we can do that, and we will be obtaining an equation. So let me directly write down. Okay, you will incorporate that, and on incorporating that, what you're going to get is, for the r part, you have theta of theta out, and you have phi of phi is out, and in the denominator you have r squared. Then you will have here d by dr of r squared, dr by dr. Okay, this will be the first part, and for the second part, what we will have is, in that case, r of r will be out, and theta, okay, the phi part, the phi of phi will be out, and in the denominator you will have r squared sine theta, and then you will have d by d theta of sine theta, d theta by d theta. Okay, so these are small thetas, and this is our capital theta. And this is the second term. Then the third term I'll have is plus, in case of phi, r of r will be out, and theta of theta will be out. Okay, in the denominator you have r square sine square theta, and then here directly you will have d2 phi by d phi 2. And then we have, as usual, we have 2m by h bar square times e minus v of psi. But what is psi that we have chosen is r of r, theta of theta, and phi of phi. So this is our translated Schrödinger wave equation, where we have used the wave function as the function of r of r, theta of theta, and phi of phi, and we have used them independently. And what do we actually want? What do we want actually here is, I want those three equations. My job is to achieve those three equations in which I have an equation of radius, I have an equation of theta, I have an equation of phi. Now let's move on from here. What would I do is, I would like to divide this whole equation by r of r, theta of theta, phi of phi. So I will be dividing this equation by r of r, and then theta of theta, and then phi of phi. And the next thing that I will do at the same time is I will multiply. So this I will be dividing. I will divide by this term, and I will be multiplying the same equation with r squared sine squared theta. So these are the two actions that I will take on this equation, and then see where we reach. So when I do that, what will happen here in this equation, you are dividing this equation by r of r, theta of theta, and then r of r, theta of theta, and phi of phi, and you have your r square here. And at the same time, you are multiplying it by r square sine square theta. So this is our first term. In the second term, you will again have the same thing. So this thing will be multiplied by r, theta, and phi as a function of, and this thing will be multiplied by r square sine square theta. So the second term is gone. So here what we will have is, I will rub this is plus here. So here you are multiplying by r square sine square theta, and in the denominator you will have r, theta, and phi. I'm trying to write it in the short form so that I can accommodate all of these symbols. And then what I have is, here I will have divide by r of r, theta of theta, and phi of phi. Okay, and here what I will have, I will be multiplying this by r square sine square theta. So here you will have 2m r square sine square theta. Okay, now I don't know whether it's visible on, I think it will be visible. You can see now we will have some cancellations over here. This theta and theta will go, and phi will go, r square and r square will go. And similarly, we can think of this, where r will go, theta will go, r will go, no, theta will not go here, theta will stay here, phi will go. So here, theta will retain, and phi will go, and r square will go, r square will go, sine theta will go, and square will go. Okay, similarly in this equation, r square sine square theta, in this parameter, r square sine square theta will cancel with r square sine square theta. Here r and r will cancel, and theta will cancel. So here we will be left with phi only. And here you can see this r theta phi and r theta and phi, they will go. So finally, we will be left with, in this case, we will be left with sine square theta by theta, okay? And here we'll be left with sine theta by theta. And here we'll be left with uh, uh, 1 by phi d2 phi by d phi 2. And then the rest of the things will come there. So let me write down that. So where we have reached it till now is we have sine square theta here divided by, it has to be r of r. R of r. Yeah, r of r. And then you will have d by dr of r square dr by dr, and then plus, it was probably sine theta alone, divide by theta of theta, and then you have d by d theta sine theta d theta by d theta. Then we will have plus, we will have 1 by phi of phi d2 phi by d phi 2, and then plus 2m r square sine square theta by h bar square times e minus v of nothing is equal to 0. So this will be our equation, and as we understand that if we certainly want some information from this equation, what is important is that we have to introduce a constant. And in fact, the people who would have done it actually, who would have worked on this problem in the beginning, they will have chosen a range of constants, and find a feasible constant is also important. So we can break down this equation only if we can introduce a constant, and we can make a transformation. I mean, suppose I take, depending on my choice, I take this part on the other side of the equation. So if I take it on the other side of the equation, I will not have a 0. What I will have, this will shift into minus 1 by phi of phi, and then you will have d2 phi by d phi 2. So what I have done is I have transferred the azimuthal angle part on the right hand side of this equation. Now I have an equation in the left hand side, and I have an equation in the right hand side. So this part I have taken on the other side. I have taken it on the other side. So what is this? This is d by dr, and this is dr. Okay, so here we have plus. Now this plus this is equal to this. Now what can I do is I can make sense out of this equation only if I incorporate a constant. Now if I choose a constant like ml square, assuming that this ml square must be equal to the left hand side of the equation, then automatically this ml square must be equal to the right hand side of this equation. So this is how we can exploit a plausible information from this equation by introducing a constant, so that a constant is a constant, and we can project the left hand side of the equation equal to that constant, and similarly you can project the right hand side of that equation equal to that constant. So when I do that, what will I get? I will get the two equations. I will get, the first one is sine square theta by r of r, then d by dr of r square, dr by dr, and then plus sine theta by theta of theta, d by d theta then sine theta d theta by d theta. Okay, then plus we will have 2m r square sine square theta by h bar square times e minus v. This must be equal to ml square. So this will frame our one equation, and the other side of the equation, which is minus 1 by phi of phi d2 phi by d phi 2, this must also be equal to ml square. Now, before we proceed down, obviously what is understood that we have got an independent equation in terms of phi. And phi is what? Phi is the azimuthal angle, and its value ranges from 0 to 2 pi. So I can write, so this equation is independent of theta and r. And then we'll proceed for breaking down this equation into the equation, the radial equation and the theta angular equation. So if I take on this equation, and I can write down this d2 phi by d phi 2, which is minus, okay, that's equal to ml squared and phi of phi. So I can have d2 phi by d phi 2 plus ml squared phi of phi equal to 0. So this is my second order differential equation in terms of phi, and I can write down its solution. I can write down its solution, and I can predict ml. I can predict the values of ml, and which you will see they will naturally act out as magnetic quantum numbers, or what we call as azimuthal quantum numbers for the hydrogen atom. So tomorrow we will proceed on from here, and we'll write down the solution, and we will try to break down the equation that we have in terms of radius and in terms of theta, and that will be our next job, because finally what we have to do is we have to come up with three equations which are r, theta and phi, they are exclusively independent of each other. You will have an exclusive equation in terms of theta, exclusive equation in terms of r, and an exclusive equation that we have in terms of phi. So we'll meet tomorrow, and we'll proceed from here. Bye. So very good morning to you, and let me continue from what we have done yesterday. Okay, and yesterday we were able to separate the azimuthal angle part, and for that we obtained an equation. It was simply d2 phi by d phi 2 plus ml squared phi equal to 0. And here we exactly got an equation in terms of the azimuthal angle. We got this equation in terms of phi. And this equation has the solution, and we can write down that solution, and we can see the conditions for ml. And ml, the constant that we have introduced here, is magnetic quantum number. We are talking about hydrogen atom. We are treating hydrogen atom using spherical polar coordinates. And you rightly remember what I did. I used the Laplacian operator del square in spherical polar coordinates. I would rather like to write it again because some of the students were absent yesterday. So the Laplacian operator in the spherical polar coordinates, I would like to write it. It was 1 by r square dou by dou r of r square, then dou by dou r, and then plus 1 by r square sine theta, dou by dou theta, and this theta is small theta. Keep this thing in mind. This is small theta, so small is, I show a curve in it, and then you have sine theta dou by dou theta, and the third term is plus 1 by r square sine square theta dou 2 by dou phi 2. And this was, this is our Laplacian operator in the spherical polar coordinates. And what I did yesterday, I incorporated this Laplacian operator in Schrodinger's wave equation, right? And when I incorporated this in Schrodinger's wave equation, then I assumed the solution as psi of r, theta, and phi as function of r, theta of theta, and phi of phi. So that r of r is not dependent on theta of theta, is not dependent on phi of phi. Then the rest of the course you can check it. You can check it in yesterday's video. So what we obtained when we took the derivatives of psi with respect to r, with respect to theta, and with respect to phi, we came up with an equation, and in that equation we had three unknowns, and what I did, I introduced a constant ml squared. So the right hand side was this, and from that we obtained this equation, and we had the left hand side. What was that? That was probably sine square theta by r square, and d by dr of r square dr by dr plus sine theta by it was sine theta by theta, and here we had r, and d by d theta of sine theta d theta by d theta. And then we have plus 2m by h bar square e minus v. And this is equal to ml square. Because this thing was the left hand side of yesterday's equation, and the right hand side I have already shown you. This was the right hand side. The right hand side was this. And from right hand side we got this equation because the right hand side was equalized to ml square. So in the similar fashion, what we do here is we have the ml square for the left hand side. Okay? So now what should be our job? The next job is, because now we have an equation with two unknowns, right? Previously we had an equation with three unknowns. Now we have boiled down into two unknowns. Okay, so let's make a little more modification in this equation. What I will do now, I will try to get things in one side having one variable and the things on the other side with another variable. So what I feel is feasible here is that let me simplify this equation more than this. If I divide both sides by sine square theta, can I do that? I can do that because my aim is now to separate theta from r. Okay, phi is already separated from the equation. So for that, what I will do, I will be dividing this equation by sine square theta. When I will do that, here I will have sine square theta, and here I will have sine square theta, and here I will have, I'm missing something, sine square theta, and here I will have, here it is sine square theta. Here it is 2m, this is 2m r square sine square theta. So you will have cancellation, sine square theta and sine square theta will go, sine square theta and sine square theta will go, sine theta and square will go. So what we will be left with is sine square theta. So here is no r square. You check it in the previous video. So what you have 1 by r d by dr of r square dr by dr, then plus 1 by theta sine theta d by d theta, this theta is small, and sine theta d capital theta by d small theta, then plus 2m r square by sine square theta and sine square theta will cancel. This sine square theta, so 2m r square by h bar square by h bar square e minus v is equal to what? ml square. But I have divided that ml square also by sine square theta. I will drift that in the left hand side, so that will become minus ml square by sine square theta is equal to 0. Okay. Now you can see this part and this part is only inculcating radius, right? So I want it separate, and the rest of the part is inculcating what? Theta, okay? And I will take that as the other side of this equation. Clear? So I will have again an equation with left hand side and right hand side, and what would I do? I will introduce a constant to separate down these two equations exactly. So for r I can write, come on, for r part it is this. For r part I will write, I'll just rearrange it now. So this is 1 by r, then d by dr of r square, dr by dr plus 2m r square by h bar square e minus v, okay? This is equal to, okay? I will take the other thing on the other side. This is equal to 1 by theta sine theta, okay? D by d theta of sine theta d theta by d theta, okay? Minus ml square by sine square theta, okay? That will become plus ml square by sine square theta. Okay, did I leave anything?
Minus.
What? This one? Yes. This one has to become minus. Alright? So if this becomes minus, so this will become plus. Okay? Now you have the left hand side of the equation and you have the right hand side of the equation. So now the point is that you have to introduce a constant, right? So you introduce a constant that works for these equations, right? So that means people have already worked for it, and what they have observed is that they introduced a constant in this case so that the left hand side is equal to the right hand side. I mean, the left hand side is equal to that constant, the right hand side is also equivalent to that constant. What is that constant? That constant is L times L plus 1. Well, L is what? It is orbital quantum number. This is what is called later on orbital quantum number. So when I do this, I will have now 3 equations in place, okay? Can you tell me the first equation in terms of phi? Ikra, come on. First equation was? It was V2 phi. by d phi 2 plus ml square phi is equal to 0. This is my first equation. Okay? The second equation is 1 by r d by dr of r square dr by dr, then plus 2m r square by h bar square e minus v is equal to L into L plus 1. Okay, right? Fine? Clear? Okay, the third equation was 1 by theta sine theta d by d theta sine theta d theta by d theta. This theta is the capital theta, and the theta that I give the curl, it's a small theta. This is the actual angle. So then this was minus, okay? Plus ml square by sine square theta is equal to L into L plus 1. Right? Now you have three equations. Equation 1 in terms of azimuthal angle, equation 2 in terms of the radius, and equation 3 in terms of the angle. Right? So now what I will do is I will take on my lecture with equation second. Right? So once we go with equation second, I know that I cannot complete it, but whatever the extent we will reach in solving equation second, we will go till then. Okay? So now let's go with equation second. What's equation second? Come on. This is 1 by r d by dr. Then you have r square dr by dr plus, come on, 2m r square by h bar square. Then you have e minus v. Okay, e minus v minus L into L plus 1 is equal to 0. Right? Fine? Okay, and now you can immediately see that this is d by dr of r square dr by dr. Then you have plus 2m r square by h bar square, and then you have e minus v, okay, no problem, minus L into L plus 1, and here I can multiply this whole thing by r, am I right? Okay, I have taken this r, okay, taking the whole thing on the right hand side, you can take capital R and multiply this with r. Now you can see you have a differential equation in terms of capital R. Okay, now see, there is another problem. What's that? I have committed a big mistake, and what's that? That is, this 2m r square by h bar is only for e minus v. So here it is minus, okay? So this may confuse you. So what should I do? I should use a curly bracket, and I should use a curly bracket here. All right. Now let us bring in L into L plus 1 into the actual bracket, okay? How will we do that? This is d by dr of r square dr by dr. Come on, plus 2m r square by h bar square times e minus v minus L into L plus 1, okay, h bar square will be multiplied and divided by 2m r square. 2m r square. And close the bracket. You got this stuck? You didn't get it? Got it? See, it's quite simple. What I have done, I have introduced L into L plus 1 into the bracket, right? So that when you go back into the bracket, there will be cancellations. You'll be left with L into L plus 1. Clear? Fine. Okay, so up to now it's okay. Another change I want to bring in here. So till now it's fine, okay? Have you written it down? Come on, come on. Let me move from here. I will write now 1 by r square d by dr of r square dr by dr plus 2m by h bar square times E minus B of R, then minus L into L plus 1 h bar square by 2mr square is equal to 0. Is it right? Come on. Is it right? This r square was here. Okay? Think of that I have taken it on the right hand side, so r square can come down. Okay? So this is 1 by r square d by dr of r. So what's the difference between the previous step and the new step is, here you don't have r, small r square. I have brought that small r square here. Is this clear?
Yes.
Okay. Now, I can, okay, so I have already talked about the potential, right? Potential energy between this electron and the proton. So what is that? So I can write down another step. 1 by r square d by dr of r square dr by dr plus 2m by h bar square times E minus. But what is the potential energy between electron and proton? Is it positive or negative? Come on. It is Q1, Q2 by 4 pi epsilon naught R. But Q1 is plus, Q2 is minus. So it's minus. Isn't it? So it is minus E square by 4 pi epsilon naught R. But that minus will be multiplied by this minus. So what you will get here? Plus. You will get plus E square by 4 pi epsilon naught R minus L into L plus 1 divided by 2mr square h bar square and close. So here I have used the equation of electric potential energy, right? Okay, so it was negative, it has become positive. Now, again, the things are going like this, and I want to introduce another variable here. And let me introduce another variable. Say I introduce a variable like rho. Okay? And this rho, I will take this rho is equal to 2 beta r. Now the question is, what is beta? For beta, what I choose is beta square is equal to 2m E by h bar square. So if beta square is 2m E by h bar square, so you can think of beta as minus 2 m E by h bar square. The point is, we are trying to simplify our equation, right? And in order to simplify this differential equation, I have introduced another variable, but that variable has a connection with r. I'm not changing it, okay? I'm connecting that variable with r, and I introduce to beta as a number with it, okay? So it's not going to change the physics of the problem, but certainly it's going to simplify our differential equation. Is this clear? Okay, so now rho is 2 beta r. Now let us think, let's go with it in a very conclusive manner. So I have taken rho is equal to 2 beta r. D rho by dr will be simply 2 beta. Right? Or another thing at the same time, if rho I have chosen, I have let it, okay? If rho I have chosen as 2 beta r, that means r is rho by 2 beta. And you can also think of r square is rho square by 4 beta square. Is this clear? Huh? And you can also think of here, d rho is 2 beta dr. Or you can also think as dr is 1 by 2 beta d rho. Right? Now what I have to do is, I have to introduce this thing in my equation. Right? And I will see to what extent my equation will be simplified. So I think, come on, I've written it down. Okay. So what was in my equation? 1 by r square. 1 by r square. But what is r square? Come on, you tell me now. What is r square? That is rho square by 4 beta square. So I will write 4 beta square by rho square. Clear? Then what I have? D by dr. So here I have d by dr. But what is dr? It is 1 by 2 beta d rho. So 2 beta will go up. So here I will multiply by 2 beta divide by d rho. Okay, then what's after that? Come on, Ikra. D by dr of what? R square. Okay, what is R square? It is rho square by 4 beta square. Very good. This is 4 beta square. Come on, come on, come on. Then I have what? D capital R, dr by dr. Come on, change that. What is dr? That is, it is d rho divided by 2 beta, but that 2 beta will be multiplied. Is this clear? Come on, go on now. What after that you have? Plus 2me by h bar square. What is that equal to? That is equal to beta square. So we have beta square. Then what we have? Plus. Come on, come on. You are not supporting me. That's a big problem. So this term is your first term, 2m by h bar square e. The second term will be what? 2m by h bar square times this. So you can tell me now. Come on, tell me now. Tell me all the terms now. So, come on, come on. Yeah. Yeah, what will be that? It will be 2m by h bar square, then e square by 4 pi epsilon naught r. What is r? In terms of rho, come on.
It's rho by 2 beta.
It is rho by 2 beta, so it is rho here and 2 beta up. Fine? Okay, then last term, that is minus. Come on, that is L. Okay, I will go with 2m by h bar square times L into L plus 1. Here you have h bar square divided by 2m r square. Close in and capital R. Is it fine? Any mistake? If I have committed a mistake, come on, tell me. Now, what am I going to do? Come on. You see this 4 beta square and 4 beta square is gone, okay? And then you have beta square here. Anything else that you can cancel here? This is 2m by h bar square. So this is 2 ones are, this is 2 twos are. Clear? Okay? So here you will have m and m will go. This h bar, it has to be square. H bar square and this h bar square will go. This 2 and 2 will go. So what will be our equation now? This is 2 twos are 4 beta square. This is 4 beta square. Then you have d by d rho of rho square. Am I right? Then dr by dr, okay, plus beta square, okay, plus, come on, this is m.
2 and 2 will also go.
Come on, come on, come on.
It will be n e square beta by pi epsilon naught rho.
So this will be m e square.
Beta.
This 2 will also go, no?
Yes.
Okay, m e square beta by
Pi epsilon naught rho.
pi epsilon naught rho
H bar square.
h bar square. You check it again. Is it fine? Yeah, it's fine. Huh? Okay. So then here what you have? Minus. Come on. So I think here you have L times L plus 1. Then divide by R square. I can keep a bracket here. And here you have R. Right? What should I do to further simplify it? I would like to divide this equation by 4 beta square, right? So I would like to divide this equation by 4 beta square. If I divide, I will get rid of this. Here I will get 1 by 4, right? Here I will get 1 by 4. So, come on, tell me now, what will I have to write here? So here I will have 1 by rho square d by d rho, then rho square dr by dr, right? And I think we have committed a mistake here. It has to be minus 1. It has to be minus beta. You can rectify it. So here I will get plus times minus 1 by 4. Am I right? Because I'm dividing both sides by beta square. 4 beta square. That's why here you have 4. Okay? The next thing, come on. So here it will be me square by pi epsilon naught rho plus me square by pi epsilon naught rho and beta and 4. Am I right? Because you are dividing it by 4 beta square. Clear? 4 beta square. Okay, then the last term will be minus L times L plus 1 by 4 beta square r. This is minus L times L plus 1 by 4 beta square r, and close it and put it r. So let us stop here, okay? We will continue from tomorrow, from here, okay? So till now we have obtained this differential equation, and then inshallah we'll see tomorrow where we'll go, okay? So bye. Good morning to all of you. So let us continue where we stopped yesterday, and I think we committed a mistake yesterday. The mistake was that I used basically the correct thing, that beta square is minus 2me by h bar square. But somehow I have wrongly written that beta is equal to minus 2me by h bar square. So this should not be considered. So beta square equals minus 2me should be considered, right? So this was the mistake that we committed yesterday, and as we understand, we are talking about the problem of hydrogen atom, and we are using spherical polar coordinates to solve the problem of hydrogen atom. And you will rightly remember that we have separated down the Schrödinger's equation into the 3 parts. We have separated it into the radial part, then 2 angular parts. One is your angular part theta, and the another one is the azimuthal angle phi. So we have classified those 3 equations, and we have been talking about the radial part, okay? And in radial part, we have reached to an equation like 1 by rho square d by d rho, then rho square dr by d rho, and then plus, I think, minus 1 by 4, then plus m e square by 4 pi epsilon naught h bar square beta, right? And I think yesterday I committed another mistake. I had put here, okay, what was here? Plus L times L plus 1.
Minus times.
Yeah, this is minus. Okay. Divide by rho square. Okay, I have divided here this thing by beta square. But beta square already existed here, 4 beta square. And that 4 beta square cancels with the 4 beta square with which you have divided it. I think that was the mistake that I committed here. So here, so in that equation, I wrote down here 4 beta square, right? But that 4 beta square cancels with the 4 beta square that already exists in the numerator. So this is multiplied by r, right? Okay. Now, let us introduce another constant. You can see that this whole thing is a constant, and let me use a symbol for it, say gamma. Say gamma is me square by 4 pi epsilon naught h bar square. Am I missing something? Rho is here also. So here you have rho also, okay? So me square by 4 pi epsilon naught h bar square beta. this whole thing I keep equal to gamma, right? So I think we are at the track right now, and let us hope that it goes well from here. So instead of this thing, I'm going to use gamma, and I would like to write down this equation again. Okay? So let me go again and write down my formal equation. It is 1 by rho square d by d rho of rho square dr by d rho, then plus gamma by rho, then minus 1 by 4, then minus L times L plus 1 divided by rho. This is whole times by r equals to 0. Okay? So this is our differential equation in terms of rho, and this equation can have the asymptotic solution, and we can think of asymptotic solution because when we take it asymptotic in nature, then rho has to be extremely large. So if rho tends to infinity, you can see that this term and this term of the equation can be boiled down. But the point is that we have to write down the solution of this differential equation. So if I go with the asymptotic solution to this equation, the solution that I will choose is r equals a e to the power of minus rho by 2, and multiply it with by another variable zeta as a function of rho. So I have this equation, okay, and this is a differential equation, and it has a plausible asymptotic solution r equal to a times e to the power of minus rho by 2 zeta rho. So I have introduced another variable, but that variable is again dependent on rho. Clear? So let's go with this equation again, and then what should I do? Okay, if I look for this equation, here I have 1 by rho square, okay? I have 1 by rho square. Then what I have? I have d by d rho of what? Rho square and dr by, so I can use UV rule here. So if I use UV, so rho square will be as it's into the derivative of the v, that will give me d2r by d rho 2 plus, come on, dr by d rho as x times the differentiation of rho square, that will give me 2 rho. I will close it, and then I have the same terms, plus what I have here, I have gamma by rho, then I have minus 1 by 4, then I have, come on, minus L times L plus 1 divided by rho square. This is all multiplied by r. Fine? Okay? So you can see immediately this rho square and rho square will go. So what you are left with? You are left with d2r by d rho 2 plus twice rho dr by d rho, then plus you have the same things, gamma by rho minus 1 by 4 minus L times L plus 1 by rho square times r. Okay, so this is our differential equation now, and its solution is r is a e to the power of minus rho by 2 zeta of rho. Right? Now looking at this solution, I have got to substitute that in my differential equation. So what is my differential equation? It is d2r by d rho 2, right? So I have to do the same thing with the solution that I have proposed for this differential equation. So what will happen? Come on. Okay, take its first derivative. I will take its first derivative. Come on. That will be, that will be dr by d rho. That must be equal to a is a constant. Get it out. Inside I will have
minus 1 by 2.
I will have minus 1 by 2 e to the power of minus rho by 2. Then I will have, I have missed something, zeta of rho. Then I will have plus zeta dash of rho e to the power of minus rho by 2. Is it right? Yes? Is it right? Okay. So this is our first derivative to the solution that we propose to this differential equation. Now, you can see I need the double derivative also in the equation, so I have to differentiate it again, right? So for that, I will get d2r by d rho 2 is A is out. Come on. Then here you have minus 1 by 2 is out. Now, again you will have minus 1 by 2. Okay, we have UV rule here. Then again we will have UV rule here. We have to do it 2 times. So here you have e to the power of minus rho by 2, then zeta of rho. Then plus zeta double dash of rho and e to the power of minus rho by 2 times minus 1 by 2. Fine? Because this minus 1 by 2 is to be multiplied to this. This minus by 2 is to be multiplied to this also, right? So otherwise it could have created the problem. So I have multiplied it by minus 1 by 2. So this part is gone. We have differentiated this part. Now let's go with another part, right? So for the another part, what you will have? So again, you will have zeta dash as x. So zeta dash of rho as x and times minus 1 by 2 e to the power of minus rho by 2 and plus, am I right? Am I doing it right? Okay, then plus, this is zeta. Why I wrote here double dash? I have to write single dash here. In this case, right? And in this case, I will write a double dash. Clear? So here you can see this is u, right? And u I have differentiated. So I got minus 1 by 2 out, e to the power of minus rho by 2 as x, zeta of rho as x. Then I differentiated v. Okay? So that's why here I have to have zeta dash, not zeta double dash. Now in this case, I will have zeta double dash because you have zeta dash already. You will differentiate it again with respect to rho. So you will have zeta double dash here. Okay. If zeta double dash is here, I will make that possible in the another term. So let it be zeta dash. The next term will be zeta double dash of rho e to the power of minus rho by 2. Clear? Do you find any kind of summation somewhere?
Yes, sir.
Do you find the 2 terms same?
Yes, sir.
Yeah, which one is that?
Minus a raised power rho by 2 zeta dash of this again by same.
Okay, so tell me the final equation. You tell me. Come on, Ikra, you dictate me now. What is the final equation here? Yeah.
It's minus a by 4 e raised power minus
Minus
a by 4
a by 4. Okay, minus a by 4.
e to the power minus rho by 2
Okay.
zeta of rho
Zeta of rho.
minus
Yeah.
minus a
Yeah.
e raised power minus rho by 2
Minus rho by 2.
zeta dash
Zeta dash of rho. Okay.
plus a
Plus a.
e raised power minus rho by 2
Okay. You should have got it common. Okay. Rho by 2.
Zeta double dash.
Zeta double dash. Okay. That's it. Okay. Now you have to add the terms from dr by d rho. Come on, Ikra. Look at that. Because in my differential equation, what I have? I also have, so this term you have written down, okay? You have to write this term. What's that? 2 rho dr by d rho. So dr by d rho is already calculated, okay? So tell me the values from dr by d rho. This one. You have to tell me this one, okay? So 2 rho I have to keep out here. So it will be plus 2 rho, yeah,
Then it's minus a by 2 e raised power minus rho by 2.
minus a by 2
E raised power minus rho by 2.
minus rho by 2, come on,
Zeta rho.
zeta of rho,
Plus a e raised power
a
e raised power
e
rho
to
by
the power of
2 minus rho by 2.
minus rho by 2
Zeta dash.
zeta dash of rho, and then there will be the other terms, okay? And then there will be the other terms. So you will see that in this equation, exponential term will be out, a will be out. It will be like a exponential times something equals 0, but this a exponential is not equal to 0. That means the thing that you have in the brackets, that will be equal to 0. So how does that look like? That's like zeta double dash of rho and
Zeta dash of
plus, no, I'm giving you the short form now, the final one, okay? Plus, not exactly sure.
It will be then zeta of rho, zeta dash of rho, and zeta double dash of rho.
I'm trying to converge it, okay? I don't want to go into that because you can do that all frisky algebra you can do at home, but what I get here is I get an equation, right? I get a differential equation in terms of zeta, and that is zeta double dash rho, and did I get, yeah, okay. Can check it here. I had done it. I can take the help. Yeah. So I'll get zeta double dash rho plus 2 by rho plus 2 by rho minus 1 times zeta of rho, right? And then plus gamma minus 1 divided by rho minus L times L plus 1 divided by rho square. And this thing is equal to 0. Okay? I have already solved it, okay? You will take the formal steps, the algebraic steps that you have, okay? And finally you will reach to this differential equation. Right? So once you reach to this differential equation, this equation has solution only if this gamma minus 1, see what we are trying to exploit here. This equation has solution only if this gamma minus 1 is equal to L plus some number n. You know L, what's L? L is orbital quantum number. We have introduced L times L plus 1 as a constant when we try to resolve the differential equation, right? And the equation that I got right now, the differential equation in terms of zeta of rho, that equation has solution only if this gamma minus 1 is equal to some L plus m. That means this gamma is L plus m plus 1. But what was gamma? Come on, Ikra. What was gamma? Yeah, but gamma was me squared by 4 pi epsilon naught h bar squared beta. This was gamma. Right? Now can I do something like this? I will bring beta here and bring gamma down. I can do that. So if I do that, what will I get? I will get beta is equal to me squared by 4 pi epsilon naught h bar squared gamma. Right? H bar squared gamma. But what is gamma? So this beta is me squared by 4 pi epsilon naught h bar squared. Gamma is what? It is L plus m plus 1. Right? Fine? Can I square on the both sides? Okay, if I square on the both sides, what will I get? I will get beta square is equal to, yeah? Come on, you will have m square e to the power of 4 divide by, I think I should go to the next. Yeah, what will I get? I will get beta square is m square e to the power of 4 divide by 4 4s are 16 pi square epsilon naught square h bar 4, then L plus m plus 1 whole square. Now do you know what is this L plus m plus 1? This L plus m plus 1 is nothing but n, what is called as principal quantum number. Principal quantum number. So we are coming close to what was postulated by Niels Bohr. We are getting those things naturally by solving the problem of hydrogen atom. So what will be the beta square here then? So beta square will be m square e to the power of 4 divided by, come on, 16 pi square epsilon naught square h bar 4 n square. Fine? But what was beta square chosen? Come on, Ikra. See the choice that we had there, right? It was minus 2me by h bar square. Let me use that. So minus 2me by h bar square is equal to m square e to the power of 4 divided by 16 pi square epsilon naught square h bar square and n square. Minus, come on. So this h bar square and this h bar square will go. Right? This 2 will come down. It will become 32. So you will have the energy. I think this m and square will go. Right? So what will be E? This is h raised power 4, yes. So it will become square. Right? It has to become square. So what we got? We got the energy that was predicted by Niels Bohr by postulating the things like the orbital angular momentum of the electron must be equal to the integral multiple of h by 2 pi. So Bohr had to start with an argument, but here you are naturally obtaining the Bohr condition. You are naturally obtaining the Bohr condition of quantization of energy. So what will be E? It will be minus m e to the power of 4 divided by 32. Then pi square epsilon naught square, then h bar square and n square. Right? And you can say that this E is inversely proportional to the square of n. What you call as higher energy levels of hydrogen atom. Right? So this is where from we achieve the quantization of energy in hydrogen atom problem. And the next part, now we presumed a solution. What was that solution? We had a differential equation. Come on. We presumed a solution. What was that? That was R equal to A e to the power of minus rho by 2. Then I used zeta of rho. Now I know I have moved on and I have incorporated two important things. One is the principal quantum number, and the another thing is the orbital quantum number. So this R I should write as a function of n and L. So R has n and L with it because it incorporates both n and L is equal to A, come on, e to the power of minus, what was rho? What was rho taken equal to? It was 2 beta R, Remember? So it is 2 beta r by 2. Right? This is the wave function of the hydrogen atom. The radial wave function I'm writing here. Times zeta of 2 beta r. So you can cancel this and this. So R and L will lead to a e to the power of minus beta r zeta of 2 beta r, where we know that beta, we know the value of beta, no? We know the value of beta. We can do that, right? So this will be our radial wave function. Fine? Now, another important part is what? Azimuthal angle. I think we should conclude that. You remember that equation? What is that? So let me write down, so you can proceed from here. You can proceed from here. You can also proceed to calculate the normalization constant A, right? You can normalize the wave function to calculate the value of A. Now, tell me about the phi. Yeah, what was that? That was d2 phi by d phi 2, was it plus? ml square of phi is equal to 0. You remember phi? It goes like this. Okay? So it goes like this, 2 pi in the plane, right? So certainly your solution will have the form of the trigonometric function. Now, if you have this as differential equation, what will be its solution?
A sine.
Yeah, you can think of that as, yeah, come on. M square plus ml square is equal to 0. So m square will be minus ml square. So m will be plus minus iota ml. So m I have chosen here for d2 by d phi 2. So what will be its solution? I can write down that solution. But I know the nature of phi. So what will be its solution? Its solution will be phi equal to a e to the power of iota ml phi. So this has to be the capital. Then plus b e to the power of minus iota ml of phi. Okay? Now this is irrelevant for me. And this is relevant for me. So this is made of what? This is made of cosine component. Cosine of ml of phi plus iota sine of ml of phi. Right? But phi is rare, it's 2 pi. So this term will give us the value for ml equal to 0, plus minus 1, plus minus 2, and so on and so forth. So ml, the value of ml can be 0, plus minus 1, plus minus 2, and so on, so forth. Clear? What is this ml called? This ml is called magnetic quantum number. And what is L called? Orbital quantum number, or that's also called as azimuthal quantum number. I think I wrongly used the word in the previous lecture. I used the word azimuthal quantum number for magnetic quantum number. I'm not sure, but I believe that I did that mistake. So if I have committed that mistake, then you will rectify that yourself. So what we have done till now is we have resolved the problem of hydrogen atom. We have taken the solution of the radial part of the hydrogen atom, and we have also looked for its solution for the equation that contains azimuthal angle phi, and we have the last equation left, which is the angular equation, right? The equation that contains theta. I think we'll do that in the next lecture, right? A very good morning to you. And today we'll be continuing our discussion on hydrogen atom. And last time we actually solved the radial part of hydrogen atom. And if I quickly revise the concept, what we are trying to do is we are trying to solve the problem of hydrogen atom, and it's feasible and it's simple if we can treat the problem of hydrogen atom uh, uh, in the respect of spherical polar coordinates. So what we have done, we have started from Schrodinger's equation, and we have used the Laplacian operator in spherical polar coordinates. And then we have used an approach of variable separables. And using that approach, what we did, we could generate three independent equations in terms of with three equations, one having a radial part, another having the two parts in terms of angle theta and angle phi. So if I rightly go back, where we stopped last time is it was something like that. We wrote down the radial part R and L as A and L, and then e to the power of minus beta R, and then zeta of 2 beta R. So I want to continue from here, and then I will take on this discussion to the angular part theta, where we will conclude these three independent wave functions. Now, if you rightly go back to beta square, I think beta square was 2me by h bar square. It was minus 2me h bar square. And in the last lecture, what we did, we calculated this E. This E, as calculated, its value is minus m square. No, it's m e to the power of 4 divided by 32 pi square epsilon naught square h bar square and n square. And this probably is, this n is called as the principal quantum number. Now, if I do the, if I use this E back into my equation, beta square equal to minus 2me by h bar square. What will I get? So I'll be getting beta square will be minus, and minus will become plus, and this 2 and 32 will cancel. So you will have beta square is m square e to the power of 4 divided by, okay, this is 32, this will become 16. So this is 16, you have pi square, you have epsilon naught square, you have h bar. See, this h bar square will multiply back to h bar square, and you'll get h bar raised to power 4, and you have n square. So I can take square on the other side of the equation, and I can calculate this beta. This beta will be then on the root of that whole thing, okay? So here I'll get m, here I'll get e to the power of 4 divided by, what's the square of 16? It's 4. Square and root will cancel, you'll get 4. Then you'll get only pi, then you'll get epsilon naught, then you'll get h bar square, and you will get n. Right? Okay. Now, this part is called a naught. It's the radius of first orbit of Bohr. So it is Bohr's first orbit radius. This a naught is 4 pi epsilon naught h bar square by m e square. This is the Bohr radius, right? It's the Bohr radius. So a naught. So what will be beta then? Beta will be 1, because in the numerator there is 1, divided by a naught n, right? Okay, so I have got beta. So beta is 1 by a naught n. Now I can write down the solution in terms of R. What is that? That is R and L and it is the function of small r, as we all know, is equal to a n l, and then you have e to the power of minus r by a naught n, right? Because for beta I'm using a naught n. Okay, then we have zeta 2r by a naught n, right? Now this thing, this zeta of 2r by a naught n, we call this log rate polynomial. Log rate polynomial. This you will have studied in your mathematical physics course, and we can write down this zeta, this log rate polynomial, that is zeta of 2r by a naught n. This is 2r by a naught n raised power l, and then L of n plus L, but this L refers to the log rate polynomial. This is 2L plus 1. This L is your orbital angular momentum quantum number, and then zeta of 2r by a naught n. So this is the expression for zeta 2r by a naught n, and I can write down r and l now. Okay, r and l will be a and l, and then e to the power of minus 1 by a naught n, r by a naught n, and then we have zeta of this, and instead of this I'm going to write down 2r by a naught n whole raised power l, then l n plus l, then 2l plus 1 zeta of 2r by a naught n. So this will be my complete radial wave function for the problem of hydrogen atom. And of course you know that this an can be calculated using the property of normalization. Now we have the third important part. Now third important part is what? Come on, Ikra. We have undergone the azimuthal part, we have undergone the radial part, and now we will go into angular part theta, right? So do you remember that equation? What was that equation? Come on. I think it was, you can check it, it was 1 by theta sine theta, then dou by dou theta sine theta, dou theta by dou theta, and then plus L into L plus 1, then minus ML squared by sine squared theta. This is equal to 0. Okay, this you will achieve by, because we had introduced the constant L times L plus 1 on the both sides of that equation. Okay, so here this theta, come on, this theta is capital theta. Keep that thing in mind. So this theta will basically go and take the part here. So what I will have is 1 by sine theta, dou by dou theta, then sine theta, dou theta by dou theta. Then this will automatically become plus L times L plus 1, then minus ML squared by sine squared theta. This thing will be multiplied by capital theta, and this is equal to 0. Look at it. So this is your equation in terms of theta. And capital theta, small theta is the function of capital theta. So you have this differential equation, and you would like to solve this differential equation. Come on, is it okay? Huh? Now, okay. So now our job is to solve this differential equation so that we can get the solution. We can get the solution in terms of capital theta. That must be our job. Can I proceed? You're always late in class. You're enjoying to be late. Come on. Come on. Now, all I will do now is, so you have this on your copy now, I can proceed? Okay? Now, I want the solution of this differential equation, and let me choose x equal to cosine theta. If I choose x is equal to cosine theta, what will be dou x? Yeah, what's the differentiation of cos theta?
Minus sine theta.
This is minus sine theta dou theta. This is one thing. What does it mean? It means dou x by dou theta is how much? It is minus sine theta. Right? Yeah? Clear? Okay. I started with x equal to cos theta, and I took its derivative, and I got dou x is minus sine theta dou theta. Then dou x by dou theta is going to give us minus sine theta. Right? Come on. If I see dou theta by dou theta, right? You can see this dou theta by dou theta is in my original differential equation, right? Now, can I write this as what you generally call as chain rule? This is dou theta by dou x by dou theta. I can do that, right? So if I can do that, this dou x by dou theta is already calculated, right? So I can use the value of dou x by dou theta. What will I get? I will get dou theta by dou theta is minus sine theta dou capital theta divided by dou small theta. Fine? Right? Dou theta by dou x. Yeah, you're right. Dou theta by dou x. You're right. Come on, you see, come on, look at this equation. Here you have capital theta, here you have capital theta. Can I think of something like this? That dou by dou theta is minus sine theta dou by dou x. Can I do something like this? Yeah, I can do it. So now I have both things that I have in my original differential equation. Where is that? This is my differential equation, okay? So I can use for dou by dou theta also. I mean dou by dou theta of sine theta, right? I can also use for dou capital theta by dou small theta. Come on. So what will I get? You got to help me here. Come on. Okay. So what I have 1 by sine theta out. Then I have what? Dou by dou theta of sine theta. What is that? Come on. Dou by dou theta. Do we have that somewhere?
Theta is minus
Yeah.
theta dou by dou x.
Yes.
Minus sine theta dou by dou x.
Where is that? Which one? Yeah, here. Oh, this is what I was looking for. So this is minus sine theta dou by dou x. Then you have original sine theta. Okay. Then dou theta, dou capital theta by dou small theta. That's minus sine theta. Come on. Check that. Then here is it. Dou capital theta by dou small theta. That's minus sine theta dou theta by dou x. Come on, tell me that. Minus sine theta. Minus sine theta. Come on. Dou theta by dou x. Closing. Right? Then I have my own terms plus L times L plus 1. Then minus ML squared by sine squared theta. This whole thing is multiplied by capital theta. And this whole thing is equal to 0. Is it fine up to here? Any cancellations? You can see this sine theta and sine theta will go. Minus will make plus with that minus. Then you have dou by dou x. Now you see you have exactly transformed it from theta to x, right? So you have dou by dou x of sine squared theta. Then dou theta by dou x. Dou by dou x of sine squared theta. Then dou theta by dou x. Then plus L times L plus 1 minus ML squared by sine squared theta. this is all multiplied by theta equal to 0. Fine? Any confusion? Okay, there is no confusion, and there should not be any confusion if I write down sine square theta plus cosine square theta is equal to 1, and that means sine square theta is 1 minus cosine square theta. There should be no doubt about it. You remember exactly where from I started when I tried to solve this equation? Come on. Ikra, what was that? X equal to
cos theta.
Cos theta. So for cos square theta, I can use x square. So I can write down this sine square theta is 1 minus x square. Right? So I can inculcate this sine square theta in my equation. And what will I obtain? I will be obtaining dou by dou x of 1 minus x square dou theta by dou x, then plus L times L plus 1 minus mL square by 1 minus x square, and this is all multiplied by theta. This is equal to 0. And this is our Legendre differential equation. This is our, we also call it associated. We call it associated Legendre differential equation. Every differential equation has a solution, right? And what will be the solution of this differential equation? We can write down its solution as theta. This theta is function of small theta. We started from here. Now this is equal to, say, I will choose some B, P, L, M, L of x. Where this P, what is this P, L, M, L of x? This is a Legendre polynomial. So this is P, L, M, L cos theta. I can write, there is no problem with that, right? And you can write this as 1 minus x square whole raised power ml by 2 mod then d by d raised power m mod dx m mod 1 minus x square. This is your Legendre polynomial, and this is the solution of the associated differential equation. And what is this b? This b is a normalization constant, and we can calculate this normalization constant using the condition of normalization. Now if you look back into the equation that we started with, this equation has in it cosine theta, it has sine theta in it, right? And the value of cosine theta ranges from -1 to +1. So if we generally think about the normalization, what we write? We write minus infinity to infinity, then you have psi star, then you have psi, then you have dx, this is equal to 1. But here I have a limiting case. I have to define the limits of integration. So I would like to write down that normalization. What's that? So I will write integral minus infinity to infinity, yeah, PL ML of x, P L ML of x dx is equal to 1. I think I should have put theta and theta star. That will give me theta square. So here I will write, here I don't have theta, I have b. Come on, come on. Remember what is theta? Theta is b times, right? So here I have b square. Am I right? Now look for this integration. Integral minus infinity to infinity. If you have PL, ML of x and PK, ML of x dx, right? Now if this L is not equal to k, for L not equal to k, your value is 0. Your value is 0. But if L is equal to K, your value is equal to 1. So that's why I have put here L and L. Clear? So what I have, B square is out. Okay? What is out? Outside I have B square. Inside I have minus infinity to infinity. Then I have what? PL, ML of x. Then again PL, ML of x dx. This is equal to 1. Right? Now the value of this integral is, so this is b square times 2 by 2l plus 1 times l plus ml factorial divided by l minus ml factorial. This is the value of this integral. Okay? The integral, oh, this is not minus infinity to plus infinity. This is from minus 1 to plus 1. Right? So when you evaluate this integral, you get the value like this. Right? So this is equal to what? This is equal to 1 using normalization condition. So what is b square then? Come on. What's b square? So b square will be equal to, the denominator part will go up, so you will have 2l plus 1 divided by 2 times, yeah, l minus ml factorial divided by l plus, what's happened? L plus ml factorial. And when you transform the square on the right hand side, it will be under root of this whole thing. Right? So I can write down the solution. What is the solution? Theta. So theta of small theta is, instead of b, what I will write? I will write this whole thing, this whole shit. This under root of 2l plus 1 divided by 2 times l minus ml factorial divided by l plus ml factorial, and then you have pl ml of x. Right? This is your Legendre polynomial. Now look at this crazy equation. In this equation, we are getting some information. And what's that information? Now see, if this L is less than ml, the overall value here will be negative, right? So you will have negative within the root. So that will be a complex solution, right? That's not acceptable. What is acceptable here? This L should be greater or equal to 1. This L should be, getting my point? This L should be greater or equal to ml. What is ml? It's the magnetic quantum number. What is L? It is the azimuthal or orbital quantum number. So I have already told you what's the longevity with this equation if we choose L less than ml, right? When you generally talk about the quantum numbers of hydrogen atom, you have that condition that L should be greater or equal to ml. And that is clear from this solution of this Legendre differential equation that we have obtained in terms of theta. So what's that condition? The condition is that this L that you will have a plausible solution if this L is greater or equal to ml. I think today I will stop at this point, right? Any queries? Any questions? Come on. No question? Okay. A very good morning to all of you who are here. Okay, so we have been talking about hydrogen atom, and we have subjected hydrogen atom to the Schrodinger's wave equation, and we have used the Laplacian operator in terms of spherical polar coordinates, and then we have gone through all those mathematical steps that were needed to separate down our theta and phi, and then we looked for the solution of these three independent parts of hydrogen atom, and the independent parts that we have had, they were in terms of radius. We had a radial wave function. We have azimuthal angle wave function. We have the theta angle wave function. So we have somehow managed to reach to the solution of those three independent parts of r, theta, and phi in hydrogen atom. Now, if I quickly revise that, what we had, okay, we started with psi as a function of r, theta, and phi, and this we chose as r of r, and then theta of phi, and theta of theta. And it was presumed that r of r is independent of phi and theta of theta. It was presumed that phi of phi is independent of the other two functions in this equation. And we obtained the solutions for theta. Okay, if I write down the solution for phi, so what was that? If I write down phi as a function of small phi, we have the solution as 1 by under root of 2 pi e to the power of I ml phi. This is the solution of the azimuthal part of the Schrodinger's equation, and this 1 by root pi comes as a result of calculating the normalization constant, right? And then we had theta of theta. What was that? Come on, do you have that? Theta of theta. It was under root of
Under root of 2ICL plus 1 by 2.
2L plus 1 divided by 2 times N minus ml.
L minus ml.
Okay, it has to be L minus ml. So this has to be L minus ml factorial divided by L plus ml factorial. And then, come on, after that?
This is Legendre's polynomial.
Yes?
PFL ml of x.
Yes.
Legendre's polynomial.
Yeah. What was that?
P of L ml.
P of L. Okay.
Yeah.
Come on. P of L ml. And then
Of x.
of
For
x. For x, I'll write cos theta.
cos theta.
Right? Okay. So this we evaluated. This is our theta of theta, and this is our phi of phi, and we evaluated r of r as well. And you can see how crazy it's going on. So we have r of r. What was that? R of r. Yeah. It was a and l e to the power of
A minus 2 beta.
minus
Beta gamma.
r by 2a naught. Was it like this? Yeah. Then you had, yes?
Zeta of twice r a naught and
Yeah, zeta of twice r by a naught. And we also evaluated, we wrote down the Lagrange polynomial for this equation. Okay? So somehow these are the solutions of the three independent parts, the radial part, and then the two solutions, what we call as angular part and theta part and azimuthal angle part, right? So what we have to do when we have to write down the total wave function, that total wave function r, theta, and phi, that will inculcate r of r, and that will inculcate theta of theta, and that will inculcate phi of phi. Okay? Right? Hello? Fine?
Yes, sir.
So in principle, you have to write down all of these solutions, and what you will have the complete wave function. You will have the complete solution for the problem of hydrogen atom in spherical polar coordinates. Now, this is over R of R, and we could see that this R of R, it has a dependence on NL. Okay, so this is your radial part. This is your radial part of the wave function. This is the radial part of the wave function. This is the radial part of the eigenfunction that we have. And then these are the angular parts, and we can realize that for angular parts we have incorporation of L and ML. So here you have L and ML. So this is your angular part. You have the radial part, and radial part gives the description of N and L. Then you have the angular part, and angular parts give us the description of orbital quantum number and magnetic quantum number. And this angular part you can find, this can be written down as a single spherical harmonics. So what we will have is, I can write down this as psi, r, theta, and phi. This is my r of r, and then I will write y, l, m, l of theta and phi. So this gives us an L, and this part, which is the angular part, it leads us to L, M, L. So my wave function that I have here, I can have a subscript for this wave function as N, L, M, L. Clear? So you have N, L, and M, L. That gives you the representation of the physical parameter that you are able to calculate treating hydrogen atom by virtue of the Schrodinger's wave equation in spherical polar coordinates. Now let us have a small deviation here. A deviation, let's go back to the problem of hydrogen atom that was dealt by Niels Bohr. You remember that? Come on, Ikra. The problem of hydrogen atom was treated by Niels Bohr, and it's called Bohr's model of hydrogen atom. So we will stand by here, okay? And what were the arguments of the Niels Bohr? The Niels Bohr argument was not pure quantum mechanical in nature. It worked on classical principles. And if you rightly remember, there had a couple of postulates. Using those postulates, we could calculate the Bohr radius. You remember? Okay, what was the postulate? The first postulate, if you rightly, let's go into the problem of hydrogen atom in the domain of Niels Bohr, which was more or less classical in nature. So what was it? It was that he treated electron as something that's revolving around the nucleus, right? And electron and nucleus has electrostatic force, right? And this electrostatic force between electron and the nucleus gives rise to the centripetal force, right? So the first postulate of Niels Bohr was that this centripetal force, it's balanced by the electrostatic force. Okay, so this is the first argument of Niels Bohr, and we can write down this mathematically. What was that? So you have the centripetal force. What is that? That is mv squared by r, right? And then you have electrostatic force, since we are talking about hydrogen atom, it has one electron, its atomic number is 1, so the electrostatic force here is minus E square by 4 pi epsilon naught R square. I will choose only magnitude, okay? Right? So this is the first argument of Bohr's model of hydrogen atom. And the next argument is what? Come on, you can see this R and this square will cancel. Right? And you will have mv square is equal to E by 4 pi epsilon naught, 4 pi epsilon naught R. What is this R? Come on, this R is Bohr orbit. This is the radius of the Bohr orbit, right? And the next postulate, yeah, come on, you remember? You don't remember that? It was that the angular momentum of the electron in hydrogen atom is simply equal to the integral multiple of h by 2 pi. So the second postulate, what was that? It was that angular momentum. Okay, I choose angular momentum, right? L, what is L? If I treat V and R perpendicular to each other, this angular momentum is mvr. Okay? And what was the postulate? The postulate was that this angular momentum is equal to n. What is n? It's that integral number, h by 2 pi. Then, fine? Come on, note it down, okay? I may have to use it. So here, I can get V here, okay? What will be V equal to? V will be nh by 2 pi m r, right? Come on. Is it fine? Now, if I write down V square, what it will give me? It will give me n square h square by 4 pi square and then m square r square. Right? Remember? Okay, this is V square. I can use this V square here. I can use this V square in this equation. Okay, so I can bring down this m into the denominator here. Okay. No. Come on. Let me keep m here. Okay, V square I can use here. What I will get? M times. I will get m times n square h square by 4 pi square m square r square. I will close it. This is equal to what? Yeah. This is equal to E square by 4 pi epsilon naught R. This is equal to E square by 4 pi epsilon naught R. Fine? Now you can cancel square of R and R. Right? You can cancel this M with the square of this. Right? Okay, you can cancel this 4 with this 4. You can cancel this pi with the square. Right? So what will be R? I want R. I will take R on the other side. So this is over R. And in the numerator, I'll have n square h square epsilon naught. I'll have n square h square epsilon naught. Okay. Divide by 4 pi m. Right? 4 pi. Anything else? 4 will go. Okay, only pi. You're right. Okay, pi m e square. You know what is this? This is the Bohr orbit. Right? This is the radius that was calculated by Niels Bohr. So you have a fixed radius. And in quantum mechanics, you don't have anything fixed. In quantum mechanics, you deal with probabilities. So, in quantum mechanics, you will have the probability of finding the electron. You will not have a single orbit for an electron. But the beauty of Bohr's model is that you will see that the maximum probability of finding an electron in the first orbital is almost equal to the Bohr's orbit. It's equal to the radius of the Bohr's orbit. Is this clear to you? Okay, this is the framework of Neil Bohr. But in Bohr model, it is more classical, right? And what we have been doing, we have been dealing the same problem by a formal quantum mechanical approach using Schrodinger's wave equation and solving the hydrogen atom problem, right? And see, I used an argument. What Bohr says? He says angular momentum is an integral multiple of h by 2 pi. What? He doesn't have any explanation for that. Are you getting my point? There is no explanation for it, but it works. It works as long as the experimental outcomes were concerned at the time of Neil Bohr, right? But here, in case when we use the same problem and we subject it to the basic formalism of quantum mechanics, we have seen, okay, we have those crazy equations, but these equations are naturally coming up with principal quantum number, n. They're naturally coming up with orbital quantum number, L. Then we have naturally coming out the azimuthal quantum number, right? These three quantum numbers are naturally coming out as a consequence of using the nature of mathematics that leads to these quantum numbers. Getting my point? Now let us try to go with a simple. We have what we have? We have psi, n, l, m, l. We have r, we have theta, we have phi. This is our wave function, and we know we have written down its solution in terms of r of r and y, l, m, l, theta, and phi. Right? Right? So if I choose n is equal to 1, and I choose L equal to 0, ML I treat 0, what I'll get? I'll get psi 1, 0, 0. Yes? Hello? Right? So psi 1, 0, 0.
सर हमारी क्लास में ना कुछ छोड़ नहीं रहा है गेट के पास शायद यूनिफॉर्म पे
I can't help it. So they should have come up with uniform that.
सर इतनी ठंड में अब आप काला काला सब कैसे पहन
That's the problem with the administration. They want to make sure that students should come.
लेकिन सोच चाहिए कब वो घर से निकली होगी कब यहाँ मतलब 8:30 निकली होती है और उसको बाहर बिठा दें
So you should complain against it. You can write down to the principal if something extraordinarily wrong is happening. How many students are out there?
फिलहाल हमें एक मुनाज़ा करना है
So can they make a call from there? Then I'll tell them to.
मैं ये बकवास है बोलो कि यूनिफॉर्म आप ठीक है कल से आएंगे
Okay. Now let's conclude it. Okay. Then after that we will do that.
क्लास में
Okay.
ये अल्फाज है क्लास में सर आप उनसे बात कर सकते हैं
Hello. जरा है वहाँ पे कोई फोन दो किसी को कौन है वहाँ पे मुझे बताओ हाँ दे दो आप दे दो
सुपर चाहिए पर यहाँ पर स्वागत है बहन हम इसके सारे कमरे कहाँ ले रखे कि मालूम इस वक्त खुदी किस वजह से आप इसको पढ़ने के आप दिया
वालेकुम सलाम ये बच्ची तो ना अच्छी क्लास होती है चला है मुझे बड़ा इम्पोर्टेंट क्लास छोड़ दीजिए
थैंक यू सर
Okay, so where we are right now. So we have, okay, I chose a special case. This is psi 1, 0, 0, right? this is over ground state of hydrogen atom, right? And this psi 1 0 0, when you calculate it, it comes out to be e to the power of minus r by a naught by pi a naught 3 by 2 times 1 by 4 pi raised power 1 by 2. Right? And this is our wave function for the ground state of hydrogen atom, and this we call as 1s state. S orbital, p orbital, d orbital. Okay, so I'll not go into the other details, but here we have 1s orbital. We have a wave function for 1s, and I can calculate its probability density, and that will be simply the multiplication. You can see this solution. Do you find any beauty in this equation? This bracketed part is the result of y, l, and l, theta, and phi. And what is it? It's a number. It's a constant. And this bracketed thing is coming out of R. It's a function. What does this tell me? It tells me that when you talk about the 1s orbital of hydrogen atom, it is spherically symmetric. Why it is spherically symmetric? Come on. Because there is no change in theta and phi. In fact, I think this is the argument that we started with when we talked about spherical polar coordinates. We chose the argument that the electron, the hydrogen atom is a spherically symmetric problem. And that's coming as a result here. We can see that this part is purely a constant. So wherever the electron is with respect to theta, wherever the electron is with respect to the phi, it doesn't matter, because it is a constant, right? So what is changing here is the radial part. The radial part. So this is psi 1 0 0, and we can have its e to the power of minus r by a naught by pi a naught cube 1 by 2. This is psi 1 0 0 whole square. So what have I calculated is the probability density, right? Now, if I plot this probability density as a function of radius, and this is my psi 1 0 0 for 1s. This is for 1s. For 1s, I find a distribution like this. And this distribution is spherically symmetric. It is spherically symmetric. Okay, I chose 1s. Now, if I choose 2s, what's that? Psi 2 0 0. Okay? And I plot it. When I plot it, this is psi 2 0 0. This is your radial function. And suppose this is 0 of the graph. I obtain a behavior like this. Now this point is called node. And you can see that this probability density is 0 at this point. That means you have a point where probability of finding the electron is 0 for 2s. Now for 3s, what I will have? I will have psi 3 0 0. And when we plot that, This is psi 300 probability square. This is my reference 0. This is my radial function. And when you plot it, you get something like this. So you have two nodes here. Say this is node at A, this is node at B. So you can go on, and what you find here, come on, you are finding different probabilities for electron to be there. So electron has a probability to be at many places at the same point of time, which is not the case when we talk about the pure Bohr model of hydrogen atom. And if I have to summarize this part, say for example, number of nodes. So number of nodes. What is a node now? Come on. Node is a point where psi is 0, while psi star is 0. Both the things are 0, right? And we can calculate the number of these nodes as, for S as n minus 1 minus L. Come on, there is another important argument. And what is that? The argument is that you have N, you have L, and you have ML. The argument is that L has to be less than N. Can anybody answer this question? L has to be less than N. Come on. The orbital angular momentum has to be less than that of N. Now what is N? Principal quantum number. So N is giving us the measure of the total energy of an electron. And what total energy of an electron can be thought of in an ideal case? It is sum of kinetic energy and potential energy, right? It is the sum of the two energies. And talking about orbital angular momentum, when you have orbital angular momentum, it has only kinetic energy associated with it, right? It has only kinetic energy associated with it. So it is quite natural to have L less than that of N. Because for N you have both kinetic energy as well as the potential energy. And for L you have alone what? Kinetic energy. So that can be an argument assigned that why this L is less than N. Now see, this simple formula will give you number of nodes. And you can calculate the number of nodes. Say, for example, if I say n is equal to 2, n is equal to 2 means 2s, okay? And L is equal to 1. What will be the number of nodes here? That will be 2 minus 1 minus 1, that's equal to 0. You will not find any nodes in this state. In the similar way, n is equal to 2 and L is equal to 0. You can calculate the number of nodes. Clear? Clear? Now, what is psi square? ML. What is it? It's the probability density. What do you mean by probability density? It means the ratio between probability and the density. Isn't it? Probability, you divide it by the density, this will give us probability density. This is what it means. And if I multiply this probability density, say psi square, if I multiply it by a small disk volume, say for example 4 pi r square, for r I will write psi, 4 pi psi square dr. You have the probability density. So you have, I can write it like this, probability divided by density, multiply it by density, will give me what? It will give me the probability. What it will give me? It will give me the probability. And this is, so So if I choose a situation like this and I plot it as a function of r, if I choose a situation like only probability, not probability density, so I got to multiply it by a small thickness where I want to talk about the probability of electrons. And this is my probability. If this is the probability, and this is your radius, this is your radial function, I should say, radial function. And what I observe is it does not start exactly from 0. When I plot it, I get something like this. Now, what will you call this point? What will you call this point for this graph? This is a maximum. What is it? It's a maximum. And what you have on this graph everywhere, you have the probability of an electron being there, because the x-axis of this graph is a radial function, right? So this is most probable radius. And you know, this most probable radius is simply equal to Bohr's radius. Now see the genius of a man. Without using quantum mechanics, his predictions are accurately matching with the, of course I should say the Bohr model is not the right model to explain the behavior of hydrogen atom, right? We can understand hydrogen atom exclusively using wave mechanics, using Schrödinger's approach. But the beauty is that when you have a plot between the probability and the radial function, the maxima that you obtain here is nothing but the radius of first orbit of Bohr, A0. So with this, I would like to stop here. Very good morning to all of you, and in continuation to the previous lecture, the previous talk, it's extremely cold out here. I think I should pick up this cap. So we will be talking about angular momentum eigenvalue equation today. So if I quickly summarize what we have done, is we have taken on the Schrödinger's wave equation and we have solved the problem of hydrogen atom based on the quantum framework. And we used all necessary mathematical approach, and we came across 3 important independent equations for hydrogen atom in terms of r, theta, and phi. And we could see yesterday when we talked about the 1s orbital, we exclusively observed that that the probabilities of electron being at different positions in 1s orbital is totally independent of theta and phi. It doesn't depend on theta and phi. And today, what we are going to do is we are going to obtain the energy eigenvalue equation, and certainly there are things that have to be taken as tutorial in this video. So to start with, I think what is the basic definition of angular momentum? And we symbolize angular momentum as L, and we define it as the cross product between the position vector r and momentum vector, right? So this is our classical angular momentum, and if I have to write down the replica of this classical angular momentum, I'll have to write it in terms of its in terms of the operators. So so for p I will be using the operator for momentum, right? And I will have an equation in terms of operators. Now, if you have to evaluate the angular momentum L, and you have to find the cross product between the two vectors. If you have two vectors, say I have vector A and I have vector B, if you have to calculate the cross product of the two vectors, you simply calculate its determinant, right? And once you calculate its determinant, that gives you the measure of the cross product between the vector A and vector B. Now, in my case, what I have is I have L, okay, and this L is the cross between R and P, and for R I have xi cap plus yj cap plus zk cap. See, I'm talking about angular momentum in Cartesian coordinates right now, okay? So, R in Cartesian coordinates is xi cap plus yj cap plus zk cap. And P you can write in terms of the operators, and you know what is Px as an operator, come on, Ikra? Yeah? It is minus IH bar dou by dou x, right? And similarly for Py cap, it is minus IH bar dou by dou y. And for Pz, you have minus IH bar dou by dou z, right? Okay, so I want to calculate this. This angular momentum operator, right? So I will have to write down the determinant. Okay, so if I write down the determinant, what will I get? I will have this L. I'll put a cap on it because I'm trying to write it in terms of operators. So this is equal to, write down the determinant. This is I, J, and K, and then you will have X, Y, and Z, and then you will have dou by dou X, dou by dou Y, and dou by dou Z, and you can keep minus IH bar outside the determinant, right? Now, you can open this determinant, right? And you can find this L as, yeah? So you will have this I, come on, you will have Y dou by dou Z minus Z by Z times, yeah, dou by dou Y, all right? So minus IH bar will be outside, and then you will have the next thing minus J times, so here I can keep I, and J times, yeah, this will be X dou by dou Z, okay, X dou by dou Z, Z dou by dou Y, minus Z dou by dou Y. Okay, this has to be multiplied by minus IH bar, and you can keep J here. And the third term that you will have is plus minus IH bar times, come on, this thing and this thing will go, so this is X dou by dou Y minus Y dou by, come on, this X dou by dou Z, dou Y, Y dou by dou X. So this is your K, right? And you have an operator in 3 dimensions. It will have 3 components. This operator itself will have 3 components, right? It will have Lx cap, it will have Ly cap, and it will have Lz cap. And in the right hand side, you also have these specified unit operators. So this equation can be true only if the coefficients of these i's, j's, and k's are equal. So what you will get, so for this L, what you have is, you basically have L cap x plus L y cap plus LZ cap. Okay, so it has I with it, it has J with it, it has K with it. So Lx is going to be equal to this thing, right? Come on. So, come on, Ikra, you have to tell me now what will be Lx, because I can't swipe it like that. So what will be Lx cap? It will be minus IH bar times
Y
yeah.
times dou by dou Z
Y times dou by dou Z
minus Z times dou by dou Y.
Z times dou by dou Y. That's fine. Okay, this is my Lx. Come on, tell me what is Ly cap. Minus IH bar. Okay, but there is minus outside. Bring that in and tell me what's coming inside the brackets.
It's then Z times dou by dou X
Z times dou by dou X.
minus X times dou by
X times
dou by dou Z
dou by dou
Z.
Z. Fine. Okay, then you have the third one, LZ cap. And what this is going to give us is minus IH bar. Come on, tell me.
X times dou by dou Y
X times dou by dou Y
and Y times dou by dou X.
minus Y times dou by dou X. Fine? Okay, so these are your components of angular momentum operators. The component along X, the component along Y, and the component along Z. But what's so natural about this is that you have these things in Cartesian coordinates. And I would like to write down this in short form. So this is, if I take this dou by dou Z minus IH bar, this will give me the momentum operator along Z, right? Right? So you can do those things. Now proceeding from here, you have Lx, you have Ly, and you have Lz, right? Now, if you rightly go back to the problem of hydrogen atom, we solved hydrogen atom in spherical polar coordinates, right? And if you have to make any comparisons of angular momentum, then certainly you have to transform these Cartesian coordinate operators into spherical polar coordinates, right? That you can take as tutorials. It's a silly exercise on at least 10 to 15 pages. What you have to do is you have to do the algebra. So what kind of algebra? You have Lx, okay? You have to write down this Lx. You have to translate it into spherical polar coordinates, and you can multiply this Lx with Lx, and this is going to give us Lx cap, right? And similarly, Ly give us Ly scar. Lz is going to give us Lz scar. Now, what is L scar? Come on. What is L scar? Yes. What is R scar? Come on, Ikra. Yes. What is R scar? If you have to find the magnitude of R in actual vectors, you have X scar plus Y scar plus Z scar. So L scar will be what? It will be Lx scar plus Ly scar plus Lz scar. So the exercise is very cumbersome because you have to translate Lx into spherical polar coordinates, then multiply it with Lx, then Ly, and the same exercise has to be carried out on Lz, and there is algebraic labor that you need to do to finally achieve L scar, right? Now the question is that the L scar that we will obtain by doing all those algebra, what will be the result of that L scar? I would like to write down that. And not to be surprised is that L scar that we obtain, as I told you, that L scar that we have obtained, what we obtain here is that L scar is minus h bar scar times 1 by sine theta dou by dou theta of sine theta, dou capital theta by dou theta minus 1 by sine square theta, dou 2 by dou 2, I should not keep theta here, okay, dou 2 by dou phi 2. Did you observe this thing somewhere as we started from doing problem of hydrogen atom? Did you observe anything like this?
That's good.
Where does this come? Where does this part come? This is the angular part of Schrodinger's equation in spherical polar coordinates. Let me revise what I said. You have independently taken L, you calculated L square, right? And when you will calculate L square, you will reach to this result. And this result is already existing in Schrodinger's wave equation in spherical polar coordinates. When you have that angular part, what do you have? Angular part. So if you have that angular part, if you will rearrange your Schrodinger's equation, you can see there that this 1 by sine theta, dou by dou theta, sine theta, dou by dou theta, this has to be plus here, okay? Plus 1 by sine square theta, dou 2 by dou phi 2, as a function of theta, and then phi of phi. This is equal to minus times L into L plus 1 times theta of theta and phi of phi. You can rearrange your Schrodinger's equation that you have written down in spherical polar coordinates, right? And you will see that the angular part, which comprises both theta as well as phi, this part is equal to minus times. If you rightly remember, we had introduced a constant to solve the Schrodinger's equation. And what was that? It was L times L plus 1, okay? So you have this part of Schrodinger's equation in terms of theta and phi, right? But what you have obtained in the upper equation, you have obtained that this thing is equal to what? Is equal to, if I transform this, it will come down as h bar square. I can take this minus on the other side, right? And what will I do then? I can use the result of the calculation of angular momentum, L cap square, which we have calculated, not completely, but that will be a part of tutorial if you are interested. If you are not interested, then you can leave it. You can directly come to the result. So I can use this part in eigenvalue equation. This is angular eigenvalue equation that I can obtain by substituting this angular part equal to minus L square by h bar square, right? So what should I do? So instead of this thing that you have in the brackets, what will I do? Come on, I will be writing down minus L cap square by h bar square is equal to minus L times L, okay, wrong. So here I have theta of theta, and then I have phi of phi. This must be equal to minus L times L plus 1 theta of theta and phi of phi. Right? Come on. You have a wave function, you have the energy, you have the eigenfunction, you have the angular eigenfunction. This is your angular eigenfunction. You have the eigenfunction, and you have the operator L cap square. This L cap square acts on the eigenfunction. You get the eigenvalues. These are angular momentum eigenvalues. You rightly remember? You have an operator. Suppose you have an operator H. You act it on eigenfunction psi. You obtain E and psi. So what is this? This is your energy eigenvalue equation, right? And what we are obtaining here? We are obtaining here angular momentum eigenequation, right? We are obtaining here what? Angular momentum eigenequation. So this is your angular eigenfunctions, and you can see this minus and minus will cancel, right? And this h bar square will go on the other side, and you can write down that this L square is equal to L times L plus 1 h bar square. So what will be L then? What will be the value of L? So what will be L? L will be under root of L into L plus 1 times h bar. So this is your angular, this is angular momentum eigenvalue equation. Now let's have some discussion on it. What is the difference between the angular momentum that you have in classical mechanics and the angular momentum that you have calculated here? What's the difference? Come on. The planet Earth is moving around the sun. It has angular momentum. If I take reference as sun, what about its angular momentum? Its angular momentum is continuous. You cannot find any angle in the space where you will say there is no angular momentum. Isn't it? You have a ball, you hang it on, you move it like that, what you will have? It has angular momentum. Can you imagine that this ball at some point of time will not have any angular momentum? No, because that's the classical world. And what's happening here? What is this L? This L is an integer. It can be 0, 1, 2, and so on and so forth. Right? And if L is, say, 1, you have a particular value of angular momentum. Then if I take its value equal to 2, you will have another particular value of angular momentum. You're not getting. Are you getting? It's quantized. This is something that goes against our physical intuition. When I asked you the problem, you said, come on, sir, it will have all possible values of angular momentum. Having a rotating body, having a body moving in circular motion, or a spinning body, it will have an angular momentum. And you cannot imagine any point in space where angular momentum does not exist. But what is happening here? Your angular momentum it's quantized. It is quantized. So the story that you have here, in terms of the electron that is present in an atom having a nucleus in it as one proton, its electron has quantized angular momentum. Now, how to generalize it more? Let's go deeper into it. Do you remember the equation in terms of phi? Come on. In terms of phi, we had dou 2 phi by, this was capital, then dou phi 2 plus ml square of phi is equal to 0. Wasn't it? Right? What is phi? Phi is the angular, this is the azimuthal angle, and its value moves from 0 to 2 pi. The algebraic thing that I was telling you, you will see there, if you will take only Lz square, this comes out to be minus h bar square dou 2 by dou phi 2. Come on, okay? So what LZ, if you take only Z component square, it comes out to be minus H bar square, dou 2 by dou phi 2. Right? Come on. Can I use this in this equation? Because I have dou 2 by dou phi 2. If I rewrite this equation, you have dou 2 by dou phi 2 plus ml square times phi of phi is equal to 0. Right? So these are your operators and then there's a constant. Okay? Now, can I write something like this, that dou 2 by dou phi 2, phi of phi is equal to minus ml square phi of phi. I can do this. Now, what is this as you have calculated LZ square? I can use that LZ square. So it will be, instead of this, I will write what? LZ square by H bar square.
Minus times.
And that too minus times. So minus LZ square by H bar square. Come on. Then capital phi, this is my eigenfunction. And what am I getting? Minus ml square. Then you have the eigenfunction. Right? So that means this minus and minus will go. This is your eigenvalue equation, right? This is your eigenvalue equation. So what will be LZ square? LZ square will be equal to ml square h bar square. Right? So what will be LZ? That will be ml h bar. Come on, what is ml? Come on, Ikra.
Magnetic quantum.
It is magnetic quantum number. And what are its values? ml, it can be 0 plus minus 1 plus minus 2 and so on and so forth. Right? So now what is happening here? When you are taking the angular momentum along z, what you are getting here? Your angular momentum along z is quantized because ml is quantized. This LZ is not going to take all the values. It's not going to take all the values of angular momentum. It can only take the values that I have given on the board. This is what is called as space quantization. What we call this as space quantization. Now, can you tell me that how can you imagine this kind of thing? Come on. You have an electron, and this electron is in the environment of a proton. Right? Can it have the orbits, the like of the classical orbits? Can we imagine it to have the orbits like that of the classical objects? No. Right? The point is why I wrote down LZ only. Because Schrodinger's equation does not allow me to calculate Lx square. It does not allow me to calculate Ly square. It allows me to calculate Lz square. But that's not the case in classical physics. Right? You have an object, you can calculate its angular momentum along Lx, Ly, and Lz. Well, what could be the answer to that question? Come on. Now the answer to that question lies in the fact that electron is not a particle. Electron is something that's described by a blurred mathematical thing known as wave function. And electron has only probabilities being present in certain portion of the space. This is why Schrodinger's equation does not allow us to calculate Lx and Ly. you can take a single direction on Z that gives us what? Space quantization. I think with this I will stop. Okay?